The Sun, our solar system's powerhouse, is the primary driver of Earth's atmospheric phenomena. Its immense energy reaches our planet and fuels a myriad of processes that shape our weather and climate. As the Sun's rays strike Earth, they are absorbed unevenly across the globe due to the planet's spherical shape and tilted axis. This uneven heating creates differences in temperature, which in turn lead to variations in atmospheric pressure. When the Sun heats the surface, air near the ground warms, becomes less dense and rises, creating areas of low pressure. Conversely, cooler regions cause air to become denser and sink, forming high-pressure zones. These pressure differences are crucial as they set air masses in motion, forming winds and driving weather patterns. The varying solar energy received at different latitudes means the equator receives more direct sunlight than the poles, creating a fundamental energy imbalance. This disparity propels the movement of air around the globe as the Earth attempts to balance this energy. Understanding these foundational concepts is vital when delving into the complexity of Earth's weather systems. The intricate dance of air across the globe forms distinct atmospheric pressure belts, each playing a unique role in Earth's climate system. These belts arise from the uneven heating of Earth's surface and the planet's rotation. Major belts include the equatorial low, subtropical highs, subpolar lows and polar highs. The equatorial low, or ITCZ, is a low-pressure band near the equator. Warm air rises here, causing frequent thunderstorms and heavy rainfall. Subtropical highs around 30 degrees latitude have descending air and clear skies. Subpolar lows around 60 degrees latitude result from converging air masses. Polar highs at the poles have sinking cold air and stable conditions. The Hadley cell is one of the most significant atmospheric circulation patterns, spanning from the equator to approximately 30 degrees latitude in both hemispheres. This cell is driven by the intense solar heating at the equator, which causes air to rise, creating a zone of low pressure known as the equatorial low. As the rising air moves poleward, it cools and descends around the subtropics, forming the subtropical highs. The descending air in the subtropics is warm and dry, contributing to the arid climates found in these regions. As this air returns equatorward at the surface, it forms the tradewinds, which blow steadily from east to west. The Hadley cell is essential for transferring heat from the equator to the subtropics, playing a crucial role in maintaining Earth's energy balance. It also significantly influences weather patterns, such as the development of tropical cyclones and the distribution of precipitation in equatorial regions. By understanding the dynamics of the Hadley cell, we gain valuable insights into the interconnected nature of global weather and climate systems. Situated between the Hadley and polar cells, the Ferrel cell operates between 30 and 60 degrees latitude in both hemispheres. Unlike the other cells, the Ferrel cell is not directly driven by solar heating, but rather by the complex interactions between the adjacent Hadley and polar cells. This cell acts as a transitional zone where air moves poleward at the surface and equatorward aloft. At the surface, air from the subtropical highs moves poleward, meeting the colder air from the polar highs around 60 degrees latitude. Here the warmer, lighter air rises over the cold, dense air, forming the subpolar lows. Aloft, the air in the Ferrel cell returns equatorward, completing the cycle. The interplay between the surface winds and the high-altitude winds in this cell gives rise to the Westerlies, prevailing winds that blow from west to east. These winds have a profound impact on weather patterns, influencing the movement of weather systems across continents. Section 5. The polar cell structure and impacts. The polar cell, the smallest and simplest of the three atmospheric circulation cells, extends from the poles to about 60 degrees latitude. It's primarily driven by the cold, dense air that sinks at the poles, creating areas of high pressure known as the polar highs. This frigid air moves equatorward along the surface, meeting the warmer air of the Ferrel cell at the subpolar lows. The convergence of these contrasting air masses leads to the rise of the warmer air, which then moves poleward in the upper atmosphere, completing the circulation loop. As the air rises and cools, it contributes to the formation of clouds and precipitation, particularly in the higher latitudes. The polar cell's influence extends to the formation of the polar easterlies, winds that blow from the east due to the Coriolis effect. These winds are relatively weak due to the low solar energy input at the poles, but they still play a significant role in the movement of air masses and the distribution of sea ice. Section 6. Trade winds. Formation and historical significance. The trade winds are among the most well-known and historically significant wind patterns on Earth. These steady winds blow from the east to the west between the equator and 30 degrees latitude in both hemispheres. They are formed as part of the Hadley cell circulation, where air descends in the subtropical highs and flows equatorward at the surface. As the air moves towards the equator, it is deflected westward by the Coriolis effect, creating the trade winds. These winds have been a critical factor in maritime navigation, playing a pivotal role in the age of exploration and the establishment of trade routes across the Atlantic and Pacific Oceans. The trade winds' reliability allowed explorers such as Christopher Columbus to traverse vast ocean distances. In addition to their historical significance, the trade winds also influence modern weather patterns. They help drive ocean currents, such as the warm Gulf Stream, which affects climate conditions in Europe and North America. Section 7. Westerlies formation and influence. The westerlies are powerful wind belts that dominate the mid-latitudes, blowing from west to east between 30 and 60 degrees latitude in both hemispheres. These winds are primarily a product of the Ferrel cell dynamics, where air moves poleward at the surface and is deflected eastward by the Coriolis effect. The westerlies are crucial for shaping weather patterns and influencing climate across vast regions. One of the key roles of the westerlies is their impact on the movement of weather systems. They act as a conveyor belt for mid-latitude cyclones, which are responsible for much of the precipitation and storm activity in temperate regions. The westerlies also play a significant role in the distribution of climates, particularly in the northern hemisphere, where they influence the patterns of rainfall and temperature. The westerlies are not just important for weather, but also for maritime navigation and aviation. In modern times, aircraft take advantage of these winds to improve fuel efficiency and reduce travel time on transcontinental flights. Section 8. Polar easterlies, characteristics and effects. The polar easterlies are winds that blow from the east to the west in the polar regions, occurring between the poles and 60 degrees latitude in both hemispheres. These winds are primarily a result of the polar cell dynamics, where cold, dense air sinks at the poles and moves equatorward. As the air moves, it is deflected westward by the Coriolis effect, creating the polar easterlies. These winds are generally weaker than the trade winds and westerlies due to the limited solar energy available at high latitudes. However, they play a crucial role in the movement of polar air masses and the distribution of sea ice. The polar easterlies can influence weather patterns in the subpolar regions, particularly during winter months when the polar vortex is strongest. The polar easterlies also affect ocean currents, contributing to the formation of cold currents that flow along the eastern coasts of continents. Section 9. The Coriolis Effect and Wind Patterns. The Coriolis effect is a fundamental force that influences the movement of air and water across the Earth's surface. It arises from the planet's rotation, causing moving objects to be deflected to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection is crucial for understanding the global patterns of wind and ocean currents. The Coriolis effect is responsible for the formation of the trade winds, westerlies and polar easterlies. As air moves across the surface, it is deflected by the Coriolis effect, creating the characteristic wind patterns observed at different latitudes. Without this force, winds would flow directly from high to low pressure areas, resulting in vastly different weather systems. The Coriolis effect also plays a vital role in the formation of cyclones and anticyclones. This rotation is essential for the development and movement of weather systems, influencing precipitation and temperature patterns across the globe. Section 10. Synthesis, global weather and climate systems. Global atmospheric pressure belts, circulation cells and wind patterns shape Earth's weather and climate. The sun's energy and the Coriolis effect maintain the balance of forces governing our climate. Understanding these systems provides insights into Earth's atmospheric dynamics. Pressure belts create distinct weather and climate zones. The tricellular model drives air and energy movement globally. This circulation distributes heat and moisture, influencing climates. Wind patterns shaped by the Coriolis effect affect climate. Winds influence ocean currents, weather systems, and climate variability.